In this section, I'm going to talk about another topic that might be optional in your course, but basically it's differentials. We used tangent line approximations in the last section using Newton's method to approximate a graph near a value. There's other ways in which a graph can be approximated by a straight line, and you can use what's called differentials. So let me just show you how this works. Consider some function f that's differentiable at x equals c. The equation for the tangent line of the graph at the point would be y minus y1 equals slope times x minus x1. But since x1, y1 would just be the point c, f of c, we can replace y with f of c and x with c here. And then the slope, of course, is the derivative of the graph at c, so that can be used for the slope. And then if you solve this for y, you'll get an expression like this. And so this is called a tangent line approximation or a linear approximation of f at x equals c. And so what's going to happen here, the closer x is to c, the closer y will be to f of c in this example. Okay, let's look at example of f of x equals 1 plus sine x at the point 0, 1. Now, we know just by plugging 0 in, the y value is 1. So that's not, that's really not anything to worry about. But what if we wanted to evaluate this function near 0? Well, we can actually use this linear approximation. So we're going to use c equals 0 as our c value, and we know f of c is 1. So, and then f of x is 1 plus sine x, and f prime of x is cosine x. So if we go back to this formula up here, f of c would be 1, and then f prime of c, if you plug 0 in here, you're going to get 1 for the slope. And then since the x value is 0, you're going to get x minus 0. So really this is just going to end up being 1 plus x, or x plus 1. Now what's interesting is it's pretty accurate if we try to estimate this function at values near 0. Like if we wanted to approximate the value of the function at point 1, then y would equal 0.1 plus 1 from this linear approximation, which is 1.1. Now note that the actual value, if you use a calculator, you're going to get 1.0998, which is pretty close. Now, the closer you get, the more accurate you're going to get. So let's get closer to 0, and we'll notice that if we use the linear approximation, we get 0.01 plus 1, which is 1.01. And then if we calculate the actual value, notice it's very close to 1.01. And then if you do the same thing for 0.001, the linear approximation is 1.001, while the actual value is basically 1.001. Now, that works as long as the value we're approximating at is near the value c, which was 0. But if we get farther away from 0, like say c equal 2, then the linear approximation starts losing ground. Notice here the linear approximation would be 3, but the actual value is actually less than 2. So we need to stick close to that c value if we use this type of approximation. Now graphically, you can look at this graph, but I just want to make a couple of points here. See, we know that at c, the value of the tangent line and the value of the function must be the same value. But if you deviate from c, say delta x units, then the value of the tangent line is going to be here, while the value of the actual function is going to be here. So the linear approximation will give you a value near the actual value, but you can see there is some error between here and here that you're going to get because of the separation between the function and the tangent line. But if you got closer, if you made delta x be very small, like right here, and you tried to approximate that value, with this value on the tangent line, then of course you would see that the error actually would become very small. So that's why when you use this, you want to use values that are close to the number c that was used to generate that tangent line equation. So in these approximations, delta x is represented by dx, and it's called the differential of x, and f prime of x dx represents dy, the differential of y. So if you let y equal f of x represent a function that's differentiable on an open interval containing x, then the differential of x is any non-zero real number, and the differential of y, dy, is dy equals f prime of x dx. So physicists and engineers kind of make liberal use for delta y and dy. Sometimes they interchange them. But you can actually use calculate error propagation by physical measuring devices. For example, if you let x represent the measured value of a variable, and then let x plus delta x represent the actual value of the variable. In other words, x is what you want it to be, but x plus delta x is what it's actually going to be. Then delta x would be the error of measurement. So if the measured value of x is used to compute another value, f of x, the difference between f of x plus delta x and f of x is called the propagated error. So this would be called the propagated error, delta y. So the exact value would be f of x plus delta x. The measured value would be f of x. And then the measurement error would be delta x, and the propagated error would be delta y. So delta x is the error in the measurement, but then delta y is the error in the actual function. So an example of this would be, let's look at an example. Let's say we want a ball bearing, which is basically a sphere, to have a radius of 0.7 inches. Now, if we know the measurement is correct to 0.01 inches either direction, we can estimate the propagated error in the volume of the bearing. Okay? Now, the volume of the bearing would be 4/3 pi r cubed, where r is the radius of the sphere. And we're given that r is 0.7, and we know that delta r has to be between negative 0.01 and 0.01. Well, to get the propagated error, we can differentiate v. If you take the derivative of v with respect to r, you get derivative of v with respect to r, and then you just take the derivative of this with respect to r, and you get 4 pi r squared. Well, dv over dr is 4 pi r squared, but if you multiply by dr, you get dv is 4 pi r squared dr. Now, if you plug in 0.7 for r, you're actually going to get 0.6158 dr for dv. So dv is 0.658 dr. But remember, dr, we can use dr, we can approximate dr with delta r. So we know that dr must be between this number, 6.158, times negative 0.01, and 6.158 times 0.01. So in other words, 6.158 dr must be between negative 0.062 and positive 0.062. Well, since that 6.158 dr is the same as dv from up here, then we can say dv must be between negative 0.062 and 0.062. So we can say the absolute value of the volume is going to be less than or equal to 0.062 cubic inches. Well, differentiable formulas for differentials are basically, you can see they basically follow the same formulas as your derivative formulas. So you basically have the same rules, but they're for differentials. Let me show you a few functions with their derivative and their corresponding differential. If y equals 5x squared, its derivative would be 10x, but its differential would be 10x dx. If y equals sine x, its derivative would be cosine x, but its differential would be cosine x dx. And then for this one, if you apply the product rule, you get minus x sine x plus cosine x for the derivative, but the differential dy would be equal to that times dx, and so forth. So you can just view the next two. Basically, you just take the derivative and then you isolate the dy by multiplying both sides by dx to get the differential dy. Now, the last thing I want to do is I want to show you how you can use differentials to approximate an example here, like square root of 16.5. Now, we know 16.5 is actually same as 16 plus 0.5. So this function is a square root function. So let's get its derivative. The derivative of x to the 1/2 would be 1 over 2 square root of x. So the dy differential would be the derivative with respect to x times dx, which is this. Okay, now we saw that f of x plus delta x is equivalent to f of x plus f prime of x times dx. Well, let's let x be 16 and delta x be 0.5. That way we would be looking for f of 16.5, right? F of 16.5. So basically we're looking for f of 16 plus 0.5, where 0.5 is the delta x. Well, from here, that's going to be f of 16 plus f prime of 16 times 0.5, the delta x. Okay, now, so f of 16.5 would be 4. F of 16 is 4. F prime of 16 is 1 over 4. And then if we multiply that by 0.5, we get 0.125. So 4 plus 0.125 is 4.125. So that's our approximation. Now, if you plug it in the calculator with the exact answer, technically this is not the exact answer, but if you approximate the answer using a calculator to 3 decimals, you get 4.062. So we can see we're about 5/100ths off here. Now, what you can consider, had we approximated 16.1 instead of 16.5, well, 0.1 would have been closer to 16 than 16.1 is closer to 16 than 16.5 is. So we wouldn't have lost as much error there. So our answer would actually have been closer had we used this method to approximate the square root of 16.1. So you can try that for yourself and compare the two answers if you like. That is it on this section. Goodbye.